Hello everyone, and welcome to this edition of IPM Holography Seminar. And today we are very happy to have Monica Kang from Caltech telling us about holographic baby universes and observable story. Thank you, Monica, and please take it away.
Thank you so much for the invitation and coming so early in Tehran time. Today I'm going to talk about holographic baby universes, which will be mostly based on the paper what Elliot just showed for this one. And throughout, to construct the baby universes in the talk, I'm going to utilize a GNS construction technique that we built in this paper, which I'll review briefly for the purpose of constructing the baby universes that's only relevant for it. And the focus here will be that I'm shifting from the Hilbert spaces into an observable, and thus the title, An Observable Story. So baby universes were coming from the idea back from Sidney Coleman, and a lot of works were done by Giddings and Strominger from the 90s on the baby universes, which is basically, roughly speaking, having a new piece of space-time manifold that becomes either attached to it or coming off of it. And when you're creating a space-time manifold as a baby universe coming from it, it can go into two different ways, which is in a connected way. So for that, the wormholes can branch out, or it can be going in a disconnected way, such as like quantum islands in an isolated manner. And for baby universe, it can then have creations and annihilations of them. And by utilizing those possibilities, we can study the physics of space-time wormholes. And throughout, by using creations and annihilations of these baby universes, and these will contribute to the Hilbert space of the theory that we're considering for the quantum gravity of the space-time. And for the Giddings-Strominger methods, they consider the third quantized model, which allows for considering the topology changes in the bulk as a Lorentzian spacetime. And in that specific model, they considered by coupling a matter field, which is an axion field, to a gravity, they explicitly show that in the quantum mechanical level, some topology changes can actually appear, and they link that directly to as a toy model for baby universes. And that then comes down to Lorentzian baby universes, and by having a big rotation, we can have a Euclidean baby universes as well. And by Rick rotation, it'll change the Schrödinger equation to the heat equation, and that'll make the time as a direction into just nothing more than an inverse temperature. So for example, we can consider 3D Euclidean space in the 4D Lorentzian manifold as a part of as just space direction. So for example, if you're considering Lorentzian baby universes, let's say in 3D space-time direction, it can have creation of the baby universe and then annihilation of the baby universe going back. Then in Lorentzian perspective, this will be nothing more than a wormhole, but it can be viewed as in 3D Euclidean baby universe, creation and forming annihilation together through the time direction in the past and the future. By that, I mean the baby universe can be just viewed as topology changes, regardless of the dimension or a direction. So as the original baby universe, they could change the topologies so they can manipulate different changes in numbers of boundaries and such, then it can create the more baby universes as the time direction goes on. In Euclidean perspective, it'll be just depending on inverse temperature flowing through. So for the focus of the talk, I'm going to talk about actually Euclidean baby universes only. And since we're in Euclidean, you don't have to worry about the time direction or Lorentzian signature, and it'll be completely diffeomorphism invariant. So from here, then if you want to have a Hamiltonian description of a 4D Lorentzian regular theory that we live in for the quantum gravity, then we can consider the 3D Euclidean geometries as a space in addition to it to have a time direction flow on top of it. So throughout the talk, it will be actually dimension independent. So all the formulations and baby universe construction can apply without considering any particular dimensions. But what one should really have in mind is that we're trying to build a 3D Euclidean geometry for the space. And on top of that, we can build a time direction to go towards the 4D Lorentzian theories. And by having this Hamiltonian description, one can then think of the basic idea of using Hartle-Hawking state, which is just a quantum superposition of 3D geometries. Then we can have this Hartle-Hawking state on to satisfy Wheeler-DeWitt equation, so that when you're using this Hamiltonian onto this Hartle-Hawking state, it'll annihilate completely. So from here, you can think of that superposition of 3D geometries used for the partition function methods. And this is nothing more than considering as an ensemble, which I'll connect back in the very end of the talk to relate back to what does it mean to have an ensemble in the methods of GNS technology. So as I was saying earlier, and right before, that we're going to actually talk about Euclidean baby universes only. And throughout the talk, I'm going to utilize two different approaches so that we can build further on for the GNS technique to work on. So one is a very familiar method of holography, and the other one is a more modern approach that's adapted recently from quantum error correction. So from holography, we know that bulk operators can be expressed as boundary operators smeared over the spatial subregions or the entire space region. And from here, we're going to utilize these bulk operators with a quantum error correction perspective so that it'll be defined only on a code subspace of the physical conformal field theory. By that, I mean, I'm going to shift really focused attention from dealing with operators as a physical objects only. And this is kind of rather important because the operators will enable us to have a local operator algebra so that we'll first be able to analyze these theories using algebraic techniques. And further on, we're going to utilize this focus to go away from the state-dependent formalism, but rather operator-dependent formalism. What I really mean by that is that, first of all, we know that local operator algebras and quantum field theories with a vacua of any kind is given as a von Neumann algebra with a cyclic and separating state. And the cyclic and separating state is an injective and not quite surjective type of a state. That gives exactly the same thing as equivalent to a vacua in the theory. And as you can tell that it's a state, and von Neumann algebra is also norm-dependent and the state-dependent type of an object, this is only possible to have a state-dependent formalism to be inscribed. However, which is very good physically speaking, because when we're measuring anything or analyzing anything to be discussed from the theory, we really want a state in the end and can manipulate with the state for correlations and various others. But in reality, when you're having state-only type of measure, it's very difficult to work with it directly, as it is easier to manipulate an operator level so that we can have like OPEs or various other things in many conformal field theory perspective. And also it is more adaptive to the tensor network descriptions and various others, as it's requiring a little bit less information. So in order to adapt to the operator pushing type of mechanism, we're going to utilize a slightly less demanding than von Neumann algebra throughout the talk, which will be C-star algebra, which is nothing more than a complex algebra with a norm that has an involution. And from here, we're going to build a physical Hilbert space that's relevant with a GNS construction technique that I'm going to explain what it is. And further on, from here, we will, of course, go back to the state-dependent description that we'll deduce out of it after analyzing everything in operator prescription. So before jumping into the GNS construction and see what that means, I'm going to give a dictionary between operator algebras and the theory of quantum gravity. So first of all, as I was emphasizing in this slide, that we always will work with a C-star algebra that's adapted to the operator level of the theory. So in order to do that, we're going to consider a C-star algebra in both bulk and the boundary, which will be mapped to the, in quantum gravity aspect, local operators in the bulk and the boundary. And from there, then we will have operator pushing map so that you can have a bulk directly giving to the boundary or vice versa. And C-star isometry will be the one that's linking between the two different C-star algebras so that you can have an isometric map from the bulk to boundary C-star algebra, which will be, after GNS construction is performed, will be given as a regular isometric map that we are familiar with a Hilbert space level, but this one does not require that quite yet. And further on, we'll have a strongly continuous one parameter group of isometries of this boundary C-star algebra, which is quite a mouthful, but it's nothing more than considering a just group of isometries. And that's nothing more than considering Hamiltonian evolution in this physical conformal field theory, or theory of physical quantum field theory. And every field theory that we will deal with in physical setup usually will have a thermal vacua, and we will consider a KMS state that I'm going to explain during the talk on what it is that gives exactly the vacua that you desire in the operator algebra language. So for here, we're going to deal with everything that's going to give you a well-described formalism in operator level method. And from here, we can build the von Neumann algebra, as I was saying earlier, that we will, so that in the end, get a state-dependent formalism after doing entire analysis. Then von Neumann algebra requires its double commutant to map back to itself. So it will require a commutant. And because of that, further on, we're going to have a commutant of these bulk and boundary von Neumann algebras to have a description in quantum gravity, which will be interpreted as the other side of the wormhole and the other boundary. So as an example, which is the most adaptive example, will be a tensor network like Happy Code or various others. So for tensor network, it's a particularly easy formalism that's completely done in operator level based understanding. So for the C-star algebra and bulk and boundary, will be exactly the same thing as considering the bulk and boundary nodes. So for example, it'll be in Happy Code considering the bulk nodes and then the dangling boundary nodes. And tensor network is defined by the operator pushing map with the tensors. So this is what really defines what tensor network is, and that will be explicitly given as a C-star isometry, as it does not require Hilbert space description explicitly. And tensor network does not necessarily require a Hamiltonian description, but in order to have a holographic theory or its understanding to be done in an analytical perspective, it'll require some sort of adaptive or corresponding Hamiltonian that describes the system. And such tensor network Hamiltonian evolution will be the one that's giving rise to this strongly continuous one parameter group of isometries of this boundary C-star algebra. And the rest of them follows as exactly through, as we still require vacua to describe a holographic theory, even coming from the tensor network systems. Are there any questions? If not, I'm going to go through to now explain what GNS construction can be in the most intuitive methods possibly. So in order to do a GNS construction, which as I was keep saying earlier, it's going to give you a Hilbert space coming from the operator level perspective, C-star algebra, into building a more physically relevant things. And that's going to give rise together with a KMS state after we perform this together, as I will explain in the end. First of all, we can prepare a state then coming from this C-star algebra. Then a state on this algebra is most possibly can be a linear functional on such that this is a non-negative real number and has an identity. And if you want to build a Hilbert space coming from it, the most intuitive idea to build such will be then defining an inner product utilizing the state and get the Hilbert space as an inner product space coming from it. Now that would be great to do so, but it'll run into a little bit of problem because the most intuitive inner product one can perform will be just directly as a multiplication, well, left multiplication specifically if we're here. Then there can exist observables when you put as a self-vanishing properties, and those will be not well defined. So an easy way to deal with that will be quotienting these explicitly out so we can have a well-defined inner product space. So we can define such and get as an inner product space coming from this algebra to prepare that state and can get the Hilbert space coming from it, whereas it acts directly by a left multiplication. So in turn, what we really have is that the GNS representation of this state is that it purifies the state into a vector state that I write as an identity vector state. And this will look very familiar in many perspectives because it looks like a vacuum expectation value from the quantum field theory, and that is explicitly correct. In fact, this will be exactly the vacua that one will be acting together with to get a vacuum expectation value, which will be satisfying explicitly as a quantity of a vector state, which will come back to this when I'm building this directly by KMS condition. So as I was saying, GNS construction will give you Hilbert space, but this will require vacua. As I was saying very in the beginning, when you have von Neumann algebra with a cyclic and separating state, the cyclic separating state is the one that's giving as a vacua, together with the operator algebra as a describing local quantum field theory. Now here, we will require such vacua to be still in the system to be through, and that'll be the KMS state, which characterizes the thermal equilibrium with respect to this Hamiltonian evolution. So in order to describe this, which I'm going to convince you that this is nothing more than having a generalization of a thermal field double system to have a GNS construction with a KMS state, I'm going to demonstrate that by first considering in a finite dimensional system and try to generalize this to you in an infinite dimensional system included so that it'll motivate you on KMS state means. So in the finite dimensional system, let's say we have n dimensions, then the algebra will be nothing more than just having an n-dimensional matrices. Then we know the Hamiltonian is generating the evolution as it will be sandwiching together with a e to the IHT and e to the minus IHT. And coming from this, we can get the thermal state as a Gibbs state. That we do this ensemble, and this will be given as a unique state representing thermal equilibrium at this inverse temperature beta. And we always utilize this trace for having a normed value for the quantity. Now this will run into a problem because traces are not always well defined. In fact, even in von Neumann algebras and infinite dimensional cases, other than type 2-1 and most generic, all the other cases, traces are not well defined. So that's a problem because then we can no longer compute this nice Gibbs state. So then we cannot define a unique state that's working with a thermal equilibrium. So in order to resolve this issue, you're going to utilize this KMS condition that's a generalized version of it, where we're given with just C star algebra and a state on this algebra. And further on, now you're going to require Hamiltonian evolution, which is nothing more than a one parameter group of automorphisms of this algebra in mathematical setting. Then for a non-negative temperature, as we're not going to consider a negative temperature, we have a state to be a KMS state if we can define a function that's analytic on the strip in the imaginary perspective of the plane from 0 to the inverse temperature, and require that to be continuous on its closure. By that, it's nothing more than what we naturally do as an analytic continuation, so that we will have a continuously well-defined understandings, so that we will be ensured to have a KMS condition satisfied, like to give rise to a Gibbs state. So what it really means is that the GNS representation allows to represent this KMS state, which is nothing more than a thermal state, as a vector state on a Hilbert space, which will be going right back to that the vector identity state that I wrote as earlier will be exactly the same thing on here. And I was saying earlier that it's going to be exactly a generalization of a thermal field double construction. So let's then consider a thermal field double construction and juxtapose it with GNS construction with KMS condition to see if that's exactly equivalent in the set for finite dimensional cases. Then first considering thermal field double construction, which is inherently coming from finite dimensional Hilbert spaces, you will define a thermal density matrix as usual that we did with the Gibbs state. And as thermal field double, the name represents, it doubles the size of the Hilbert space so that we can construct a purification of this mixed density, so that it'll become H cross H as a doubled Hilbert space. So in this very doubled Hilbert space, then we usually traditionally write the thermal field double as the vector state to be constructed as a purification onto your choice of eigenbases of the Hamiltonian. The eigenvalue has an explicit dependence of the inverse temperature and the energy eigenvalues. So this is nothing more than exactly purifying a mixed density to the particular choice of an Hamiltonian eigenbasis. Now, just to juxtapose and highlight it, we're going to consider a finite dimensional context for this Hilbert space for the GNS representation. Then when we're having the energy levels to be degenerate, then for the Gibbs state, the thermal density matrix is invertible. And that means it means nothing more than that the ideal of the GNS representation is trivial. Then we can consider the Hilbert space, which is directly constructed out of this algebra, but this is exactly isomorphic to H cross H. So it's really doubling explicitly. Then the density matrix is now represented as a vector state. What do I really mean by that is the GNS representation is identical to the thermal field double construction in this particular setup of a non-degenerate finite dimensional case, so that it's purifying and doubling the Hilbert space. So the key point that I want to deliver by this analogy is that thermal field double construction transforms any mixed thermal state into a vector state, which is a point of having this construction to be allowed. And this is explicitly the same thing if you're considering both finite and infinite dimensional cases as a generalization. For the Hilbert spaces, then you can do exactly identical things by considering GNS construction with a KMS state. Now, utilizing these.
Before you move on?
Yes.
Okay, so I have a very naive question. These KMS states that you're considering are thermal states with respect to the evolution by the modular Hamiltonian, right?
Yes.
These modular Hamiltonians are usually not local. Is there any need for more specifically concentrating on states that give us a thermal state with respect to a local modular Hamiltonian, or any KMS state would work?
Even though you're considering any local type of theory construction with modular Hamiltonians, if your Hilbert space is explicit infinite dimensional, you cannot utilize the thermal field double mechanism anymore because it has to be finite. Otherwise, you cannot determine that. The modular Hamiltonian method is just, in this perspective, just generalizing so that you can apply to infinite dimensional mechanism as well.
I see. But I mean, in this infinite dimensional setting, can we talk about the evolution being local or non-local without talking about the modular Hamiltonian?
I think you should always consider modular Hamiltonian, at least, unless you're doing explicit construction with a cutoff. But the whole idea here is that it will be nice to not consider cutoff and consider modular Hamiltonian instead, so you can have a nice formalism to understand it.
I see. Okay, thank you.
So now with the GNS construction on the back of our head, I was only trying to use this in the purpose of this baby universe talk so that we can utilize to understand baby universe. So in the baby universe then so far, in all this formalism to the GNS, it required a C-star algebra as an understanding to an algebraic level to have it work it in the level of the operators. Then in order to do so, we need to first try to construct a baby universe algebra. And in order to construct the baby universe algebra, let's then try to understand the baby universe operations that's going to give rise to baby universe algebra to construct further on and understand its implications and its physics thereof. The baby universe then can have creations and annihilations, as I was saying earlier in the very beginning. And in order to determine the operations around here, then we can have a connected sum and gluing for the creation and annihilation respectively. First of all, we can have a connected sum to a maybe empty component of spacetime or a regular spacetime. What I really mean is that the baby universe creation is going to be represented by the operation called connected sum here, which can have two different scenarios, as I was saying earlier. One would be that the connected sum will be performing with a pre-existing piece of a space-time manifold. Then that will be easy because you can then consider pre-existing space and the baby universe created, and then you can just do the connected sum together. So here is depicting the operations of connected sum. These blue disks are removed from the hyperbolic handle bodies, but these red conformal boundaries. Then these handle bodies are glued together via identifying these disks together along the holes. And for the pre-existing piece of a space-time, we're going to put one here, and then you can just glue it together. Back to this. But I was also saying that baby universe can also live on its own, like the isolated islands can also form. But as a theory perspective, if you do not know that baby universe is created, that would be not really okay as a theory, because you need to know that it is formed, even though it's not connected to a pre-existing piece of a space-time. So in order to do that as a holistic for the theory, to acknowledge that it has been created, we're going to now do a connected sum with an empty space-time here, so that it will be as a whole together collected to give rise to an algebraic construction of the baby universe without disaccounting these type of living alone type of baby universes. Now, annihilating baby universe is a lot easier since you're going to have just two red conformal boundaries of the two different hyperbolic handle bodies to be glued in right back together, so that baby universe will just annihilate by doing this operation. Now, these two are the then responsible baby universe operations for creations and annihilations, as it did in the Giddings-Strominger for the Hilbert space perspective. But these operations then act at the level of topology of the space-time manifold. Then you might think that, then you can have many ways to perform them and however many you want. But this is not quite the case, because as I was saying in the very beginning of the talk, we have diffeomorphism invariance to be satisfied for the theory of gravity that we have. So these operations, it turned out to inherit a very nice structure due to diffeomorphism invariance. So for example, we can have the connected sum of two manifolds, and these are going to be defined very uniquely in a diffeomorphism invariant theory. So what I mean by that is that you can have a large number of possibilities on performing this connected sum. And this will be completely gauged out by having diffeomorphism invariance. And this will be actually even better than just that, because these operations are going to be mutually associative and commutative up to this diffeomorphism. So from here, what we can deduce is that the outcome of these operations, connected sum and gluing, responsible for creation and annihilation of the baby universes, performed in a row, will not actually depend on its order or the place where they are performed. So you don't have to trace or track individually, but rather you can just do it all holistically at the same time, which will be giving a lot of ease in terms of understanding the baby universe algebra. So then now we have these operations and understanding already in mind, we are finally ready to have the baby universe algebra to be constructed. So the whole theory perspective that we'll have a theory of quantum gravity for the observables that we have, then it'll have the baby universe contributions and the rest reservoir contributions. And the abelian baby universe algebra that we put here, because the operations are mutually associated and commutative, these properties will ensure it to be an abelian C-star algebra. And the reservoir algebra, as we're considering only tracing as a topology changes of the space-time, then we can write it together with an algebra and the conjugate of this algebra coming from the summing over all possible different boundary structures. So from here, then we can build the entire algebra of the quantum gravity of the theory that we want to know of. And further on, we actually need to know now a reference state to this Hilbert space with a vacua, because in order to understand the vacua, which we're going to utilize now the technique of GNS, we explicitly need to then require a reference state, which will be working as a KMS state. And from here, then we're going to perform GNS representation then with respect to an abstract state on the algebra of observables. By that, we're going to then utilize this as defined to be an expectation value functionals. In the theory of quantum gravity in the bulk that we're going to consider as a space-time, this role is explicitly then played by a gravitational path integral. And these will be associating to each bulk operator with its expectation value by summing over all geometries, as we're going to deal with explicit partition function that integrates over all possible geometries. Then from here, we can apply the GNS constructions together that we briefly recapped before. Then we're going to have a vacuum as a KMS state that's going to be acting on to become a state. And the Hilbert space can be formulated, as I was covering earlier, with the baby universe algebra, but modding out by all the self-vanishing type of state ingredients. So with this in mind, then under this setting, we're going to then utilize two different aspects. That baby universe algebra is a commutative C-star algebra, and now we have a state that is a state on this very commutative C-star algebra. And under this setting, by utilizing Stromer's theorem, who's a mathematician, that we can infer that the GNS representation of this baby universe algebra arising from this state has dimension 1. What is identical to this will be saying that the Hilbert space of this baby universe is of one-dimensional. And the Stromer then will imply that this is equivalent to saying that this very GNS representation of baby universe algebra is then irreducible. Then what does it really mean to have a state on the C-star algebra to have an irreducible representation? It turned out that it'll have actually very nice physical meaning in terms of purity. So in order to really know that, we should look into the space of states on this very C-star algebra, which will be the baby universe algebra. And the space of states is given as the space of expectation value functionals on this very algebra. And the convex combination of expectation value functionals are then also expectation value functionals back itself. So from here, we can infer that the space of states on the C-star algebra is a convex space, which is coming from this space of states of the baby universe algebra. And since it's a convex space, it definitely has extremal points, which are the points that cannot be expressed as a convex combination of two other ones. And this is nothing more than an abstract way of saying that it's a pure state, it's just a state that cannot be expressed as a statistical mixture of other states. So more concretely to say these, under this setting, now we have established an equivalence that the GNS representation of this baby universe algebra arising from the state is of dimension 1, which, as I was emphasizing before, means that the Hilbert space of this baby universe is of one-dimensional. Is equivalent to saying that this very GNS representation of this baby universe algebra is irreducible. And what it means by that in terms of physical understanding is that this state is a pure state. Now, more precisely, since we need to really understand what this means, the space of states on the C-star algebra, which is the baby universe algebra, is a convex space is what I was saying. And it's actually a little bit more than just a convex space. By that, it has a property that every state on this baby universe algebra can be written as this, which can be written as then formal integral over the space of pure states for some measure. And in terms of then GNS representations, we can translate this into having a direct integral decomposition of the GNS Hilbert spaces so that it'll be integrating over this irreducible GNS representations, which for here, for our sake, it will be then one-dimensional Hilbert spaces as they will be baby universe Hilbert spaces. And these will correspond to a member of the ensemble of theories averaged over. So what it really means by that is that the GNS representation of this baby universe algebra has dimension 1 if and only if it is not an ensemble. So what I mean by that is that the baby universe hypothesis coming from, which is given as the baby universe Hilbert spaces is of one dimensions, is valid if and only if baby universes is not described by an ensemble. So from here, what we can really see that is that the state is pure is identical to saying that this ensemble contains one element, so that it'll be reconferring that that'll be the correct way to view it. So from here, we need to then understand the baby universe hypothesis to be understanding with respect to gravitational path integral formalism, and finding the minimal restriction to have this dimension 1 hypothesis will be then requiring the restriction of the state to the baby universe algebra to be pure. So what I really mean by that is that now the state will have an explicit restriction coming from the baby universe perspective, and then it'll decompose out to be factored individually as a tensor factor. This sounds very familiar to us because this will mean exactly the same thing in the gravitational path integral, that it factorizes. So from here, in other words, that the CFT boundary is then factorizing completely separately from the baby universe contributions that we changed by coming from the topology changes considered. So that means that the formation of the baby universes cannot be influenced by the boundary observables. And that's explicitly what would be conferred coming from the McNamara-Vafa and Merolf-Maxfield. So now putting these together, let's say then we have quantum gravity algebras to be represented through the reservoir algebra and the baby universe algebra, with this baby universe algebra being abelian. Then the GNS representation of baby universe algebra induced by a state is of dimension 1, which is equivalent to saying the Hilbert space of this baby universe is of dimension 1, if and only if the restriction of the state to baby universe algebra is pure. Now that is quite the mouthful. So we need to then change into understanding as a physical validity conditions to ensure when this is possible to be having a one-dimensional GNS representation. Then we can just put it as 3 different conditions to be satisfied. Then this will definitely ensure the GNS representation of the baby universe algebra to be one dimensions. So first one will be that baby universe algebra is abelian and your algebra of the quantum gravity is given by the reservoir algebra with the baby universe algebra proportions. And the next one would be that the state is a pure state on this quantum gravity algebra. And further on, you would require this algebra to be, you'll require the state to be a tensor factoring so that you can have a restriction of this baby universe algebra onto the state to be pure. So let's say we believe all this is true and satisfied to be correct, so that it will be indeed a one-dimensional Hilbert space for the baby universes. Then we should understand what should such a state really look like. So here I'm going to recall explicitly that one of the most important assumptions that we used was that, or not an assumption, that a fact that we derived is that the baby universe algebra is actually an abelian C-star algebra, just given by considering baby universe creation and annihilationist operations. Then the state on this baby universe algebra is pure is exactly equivalent to saying that it is multiplicative. By that I mean it'll divide individually into this format together. And this is called a character of baby universe algebra in mathematics. So when having this purity condition, then this is exactly equivalent to saying that the correlation functions of the effect of adding 2 boundaries factorize. And these are given by Merolf-Maxfield and McNamara-Vafa to be also satisfying, and they provide that it is because, or they argue that this is coming from miraculous cancellations of contributions of different topologies in the bulk. Then let's really see how this is just being granted by having the character theory approach. So from here, any abelian C-star algebra, which will be the baby universe algebra that we consider, is exactly isomorphic to the algebra of complex valued continuous functions on a locally compact space. And that has to vanish at infinity. And when this space is compact, that means it's identical to having the algebra to contain a unit. And such type of space is called a Galfond space of the algebra. And why do I mention this? Is that because this is actually the reason why we're granting the miraculous cancellations always from this character theory perspective. So by looking into the space of pure states, which is nothing more than the alpha parameters on this algebra, is identical to or corresponding to evaluation functionals on this X, which is in fact directly isomorphic to X itself. As a result, we can then confer that the space of characters on this algebra, realizing the miraculous cancellations in the gravitational path integral, is nothing more than having it explicitly corresponding to a Galfond space of the algebra itself. And what is important to realize here is that while the then space of states on this abelian C-star algebra, as the baby universe algebra, is extremely large, the moduli space of states that satisfy the baby universe hypothesis, or just the alpha states, is reduced to a locally compact space, and that's X. Then what we can really see that is that out of the many possible path integrals that we can do, the baby universe hypothesis, which is that the Hilbert space of the baby universe is one dimension, singles out a very small amount of the chosen ones, and that cancel all the observables in the algebra baby universe is enough, so that they all really collapse to a trivial tensor vector at the level of the Hilbert space. Is there any questions? Okay. So by utilizing these, I'm gonna now give two different examples to understand what this can really give rise to a more physical and context for different type of theories. The first example I'm going to give is a topological theory, which is also considered in Merrill-Max field. And in this setting, there's only one boundary structure. So the B that I used for the reservoir algebra that I summed over to construct the quantum gravity algebra, that B is just simply 1. And there is only a boundary inserting operator, which is a Hermitian here. Then conjugate boundary is indistinguishable from adding a boundary on its own. Then the idea is to identify this Z with a real variable function fx is equals x, which is obviously invariant under complex conjugation. Then we can look into the algebra that it generates together with considering the constant function together. Then we can consider the state to be representing the gravitational path integral defined in this algebra by this topological theory will be nothing more than giving together with the moment map that obeys under the Poisson law, so that we can write just explicitly as a Poisson summation for the state. Now, if you look into this, this will have a little problem because this function fx is equals x, or a constant function, does not vanish at infinity. And I was saying earlier, it'll require to vanish at infinity with a locally compact space. However, this is still okay because I didn't tell you that we can also utilize exactly the same methods to build a pre-Hilbert space instead, and then take a completion to get the Hilbert space. And it'll be working exactly in the same manner. Now, if you're considering to just get as a pre-Hilbert space structure instead, we can perform the GNS construction on the now polynomial algebra generated by this function without requiring the Hilbert space structure. And it's actually okay to do so because all squares of these polynomials will have a finite expectation value when integrated against this Poisson density. So because of that, we will have a well-defined and nice pre-Hilbert space and take a completion to get the Hilbert space in the end, which you will still find it to be very collapsing. And here, the Galfond space is a real line on its own. And coming here, let's then consider end of world brains to consider a dynamical boundary. If you do so, now the same thing will apply exactly in the same manner, except that now Galfond space will require a product of real line together with a space of matrices coming from this dynamical boundary, which will add a structure of slightly more geometric structure that we didn't consider up till now. Another example one can deal with is a QCD theory connection with a theta vacua. So for here, then we can consider a boundary inserting operator that is the dagger is equal to the inverse instead of on its own, so that'll be unitary. Now, because of this, this can be achieved by taking the conjugate boundary operation as a gluing against its corresponding boundary, so that the gravitational path integral is now performed over topologies with one less boundary than before. And by having this will inherit the group structure now, since we have it together equivalent to the inverse. And let's call this group structure to generate G as a group of the C-star algebra. Then the corresponding group algebra can be written together with this generator of this group that one can have, which is finite numbers, and put it as a combination altogether so that we will explicitly have this group algebra. And from here, let's consider a group that's going to be formed coming from considering k different boundary structures. So in the back of the talk, when I was considering the reservoir algebra to sum over all possible boundary structures, now we have all the way up to k. That means we're going to have now a group structure to be z to the k with a k different generators we have to consider for this group. Then this group will generate a C-star algebra with this group, which is isomorphic to the algebra of polynomials with k variables now with positive and negative powers. And further on, we should endow this with an involution, which is nothing more than taking the group inverse of each group element and the complex conjugate of each scalar, and also further with a norm, since we need to have a normed space to require it to consider a C-star algebra. And by requiring these, we're going to define a baby universe algebra to be a group C-star algebra that we require it to be as this. One interesting thing to remember is that the simplest case that we can do will be a one boundary structure, so that'll be k equals 1. And then this group algebra will be exactly isomorphic to the space of Laurent series in one variable. Then the Galfand dual of this C-star algebra, of the C-star group algebra, will be nothing more than considering as a Pontryagin dual of this group. So when we're considering the example of just k boundary structure, so that there will be a group to be z to the k, and there's k different free abelian generators, then the Galfand dual of this will be a k torus, because there will be each generating k different generators, and when the k boundary structures are allowed, each of the c of zk will be isomorphic to the algebra of polynomials with k variables that induces of individual circles, so that we're going to have k copies of a circle, so that it'll be a k torus for the k different boundaries. So for example, when you're considering a simplest case, as I was saying earlier for it, then k is equal to 1, that Galfand dual is nothing more than a single unit circle. Now further on, let's now explicitly consider for this example of group to be z to the k with an observable that lies into this quantum gravity algebra. So if you're taking the now observable into the quantum gravity algebra, that will have a component coming from the reservoir algebra and the baby universe contribution. And coming from it, let's say this is coming from the reservoir algebra, and this one is coming from the baby universe contributions. Then since we have a group C-star algebra for the baby universe algebra, which we can write with k different independent generators, as we have allowed k different generators with the k different boundary structures, then we can go through the baby universe action under this to give rise to this under the group algebra. Then coming from here, this transformation will give you a pure state on this state, which will be identical to a character on this group algebra of z to the k. And as earlier, as I was saying, when you have a purity, it's identical to having a character, and it will be then multiplicative property to be ensured. So by utilizing this, we can have a multiplicative property to give rise to this, which will have individually divided up, and then that's going to give rise to the phase. So from here, then the action of the baby universe transformation is now adding this explicit phase that's parameterized by this alpha parameters that spans the Gelfand dual of the U1 to the K. And this phase 2, the action for the gravitational path integral on an observable, which goes back to the story of observables to understand this different type of baby universe algebras. Then we can interpret this group of baby universe transformations as a global symmetry group, and then associated alpha parameters as the topological charge. Now, this is then very close to the context of the non-abelian gauge theories, at least in Euclidean signatures. In fact, the non-triviality of the homotopy group of this pi3 being Z, where we have this group to be any compact connected simple Lie group, for example, for the one of the QCD that we're considering, then leads to similar phases in the class of path integrals. So these phases terms are of the form of the e to the in theta. So this theta is the vacuum angle of the QCD theory that labels superselection sectors. And in our setup, those are exactly equivalent to the alpha parameters, which was giving irreducible GNS representations. And further on, it have this winding numbers. If you go back to it, this was the alpha parameter, and these winding numbers were then exactly tagging the number of boundaries coming from the different counting of boundaries that we did. And the conjugate boundaries will be counted negatively, added by the gauge transformation. And utilizing these methods, we can now further possibly look onto various other implications or applications utilizing this new GNS technology. So far today, entirely we did in the context of Euclidean theories. C-star algebra on its own does not have any Lorentzian structure. So we can try to build as a 3D Euclidean type of quantum gravity system, and then have additional time direction by considering perhaps Kahn's co-cycle or modular flows together with additional time. We should be able to then utilize a better understanding of the Lorentzian theories. And these type of GNS construction has been utilized for the tensor networks. With Elliott Gesto, I looked into pentagonal tilings of the happy code, and we could analyze a Hamiltonian description and further on analyze to get particular type of decaying correlator functions for a particular aspect, and could find different type of physical implications and analyze in different setups. And one can utilize this further for more complicated happy codes by mixing into hexagons, or more difficult and complicated but more relevant setup of tensor networks, perhaps more towards the holography, such as hyperinvariant codes or various others. Further on, we've also used this GNS technique to prove the exact theorem of entangled vector construction to be equivalently rising to the equivalence of the relative entropy between bulk and the boundary, also known as JLMS formula. And one can try to now utilize this to understand approximate version of this theorem. By approximate, I mean more incorporating gravitational approximation theorem. By that, I mean to incorporate more of a generalized entropy that is beyond just the order of 1/g Newton. And further on, one can try to understand the meaning of quantum extremal surface that can potentially exist in the infinite dimensional Hilbert spaces, and study what can be possible to be grabbed thereof, or further more on to relative entropies, one can be understood together in that setting. Thank you for listening, and if there's any other questions, I'll be very happy to answer.
Great, thank you. If you have any questions, please go on.
Hi, Monica, can I ask a question?
Yep.
Thank you for your very interesting talk. My question is related to the ensemble average interpretation. Really, in two-dimensional quantum gravity, we know that we have some ensemble average interpretation. but you say that in higher dimensions, it seems no ensemble average interpretations appears. My question is come back to the crucial difference between the two-dimensional and higher dimensional analysis of GNS construction. So what is the difference? Why in two dimensions we have an ensemble average, but in higher dimensions, no ensemble average exists?
That's a difficult question. Well, I think as a string theorist, we all agree in the higher dimensions, we do not expect to have an ensemble, I think. But I think more interestingly in GNS approach, what it really tells us is that when you're considering as a topology changes, which you can interpret different type of boundaries to appear and not, if you're considering in a higher dimensional perspective, it doesn't necessarily grant you to have ensemble pictures to be alive at any time. At some point, you might be able to do so. I think it's coming from the fact that in two-dimensional analysis, we're not utilizing in a very mathematically rigorous way of doing so. For example, even replica trick is not mathematically rigorously done, and it might have a lot of subtleties, and it is definitely not carrying over so easily to the higher dimensional perspective. I think it's probably due to having additional degrees of freedom and hard to deal with it.
I see.
I hope that answers somewhat.
I see. Thank you. Also, another question. You say that, just to be sure that I understand your point, you say that the GNS construction of the baby universe, Hilbert space, is one-dimensional. And it's come back to the diffeomorphism invariance, or it's because of some extra constraints? Is it really come back to?
If I understand your question correctly, are you referring to that diffeomorphism ensuring us to give an abelian C-star algebra for the baby universe?
Yeah. Is it correct?
Yes, that's very important, because if you do not have the diffeomorphism invariance, you will not be restricted to have an abelian algebra for the baby universe. Then it will be very unlikely to be satisfying any of the conditions to ensure dimension 1 for the Hilbert space of the baby universe. I mean, it's not the only requirement, but it plays a huge role.
I see. Thank you.
No problem.
And I also have another question. So you mentioned that we should think about these baby universe algebras as a group C-star algebra of a global group G. How should I think about the states that spontaneously break this symmetry?
Like this one, right?
Yeah.
Yeah, this is a particular interpretation trying to now link back to the topological theories. So first example was a purely topological theory. And for this setting, you're now linking as an analogy to the QCD setup. And since we have a group of baby universes as a transformations, then we can now, as a high energy theorist, what we can naturally do is that, we have a symmetry group. So how do we understand what this group structure attached? And usually it gives rise to topological charges in our setup from Yang-Mills. So I'm making that analogy coming from the QCD with the synopsis that we do in GNS technique approach. And this is kind of already done, but not in the physical context so much in AQFT. It's just that I'm linking more in the context of physical settings.
Are there any more questions? One. not, let us unmute ourselves and thank Monica for this great talk. Thank you so much.
Thank you so much for inviting me.